folks. I hope you're doing great. So in this section, we want to talk about optimization problems. It's a particular type of word problem where you use calculus to either maximize or minimize a particular situation that you've been given. I have some guidelines to help you out. So the first step in solving an optimization problem is to assign symbols to all given quantities and quantities to be determined. For example, we usually use A to represent area, or N to represent a number, or P to represent perimeter. And you certainly don't have to use the same variables that I do, because our answer in the end is not based on what variable we select, of course, but answering the question. But, I'll try to pick the most obvious letters, but you have to pick some kind of variable to represent your values. The next step, you're going to determine two equations that represent the given information. Now, I don't want to tell you 100% of the time you're going to have two equations. There are certain types of problems that are somewhat already set up for you where you really only have one equation that you're supposed to maximize or minimize, but the majority of the time you're setting up two equations. It says one of the two equations will be maximized or minimized. So of the two, one of those guys, you're going to find the maximum or minimum of the equation. The other is called the constraint equation, the one that you're not going to maximize or minimize. And I'm going to tell you, your book uses different words for that. The equation that is maximized or minimized, they call the primary equation. And then the constraint equation, they call the secondary equation. But fact is, I really like the idea of the maximize and minimize equation and the constraint equation. And you'll hear me use those terms as we go through because to me it just makes a little bit more sense. Third step, here's what we're going to do. We're going to substitute for one of the variables in the equation to be maximized or minimized because you're going to have more than one value that varies. But that constraint equation, and that's why it's called a constraint equation, puts limits on that, and you solve for a variable in that to substitute in the other. And I'll give you an example here. It says, if P equals XY, let's just say you have P equals XY is what you're trying to maximize, or no, that's your constraint actually, and you're maximizing A equals X times Y. So maybe that's area. Then you're going to solve for X or Y in this first equation, the P equals XY, and substitute for that X or Y in the second equation. Now the whole idea is that the equation you're maximizing or minimizing only has one unknown value, one variable in the expression or the equation. Okay, so that's the goal. Step 4, determine the domain of the equation to be maximized or minimized. So after you do that substitution, you want to look at the domain of that particular function. Notice it says this will help you decide if the answer values you arrive at in step 5 are consistent with the constraints of the problem. You're going to have a domain. It says do not forget to consider endpoints because you're looking for absolute maximum and absolute minimum. So that domain is going to be important when you think about endpoints of your function. Next step, evaluate the derivative. You knew that was coming, right? This is in chapter 3, which is applications of the derivative. And we want to evaluate the derivative so we can find the maximum or minimum, whatever is being asked. And you're finding an absolute max or absolute min. So if you recall, going back to our very first section in the applications of derivative section, it tells us how to do that. You take the derivative, you find the critical numbers. Critical numbers come from setting the derivative equal to 0 or where it's undefined, and then you take those values along with the endpoints, plug them into the original function. The biggest value is your absolute max, the smallest value is your absolute min. Step 6, it says determine the absolute max or absolute min by substituting the endpoints. Actually, the story I just told just then covers that as well. Okay. Step 7, there's typically another variable that needs to be determined after you have determined the value for step 6. To find the value, simply substitute your answer from step 6 into the constraint equation. In other words, you might be missing, if you're dealing with X or Y and you found X, well, then you need to go back and find Y. Okay? So there you go. there's guidelines. So as we do these problems, we're going to try to make sure we follow the guidelines every time, and that will give us our solution to our optimization problem. Okay, so you ready to try a problem? We're going to start small. It says find two numbers whose difference is 100 and whose product is minimum. So remember what we're trying to do. We're trying to come up with two equations to represent this information. One of them would be your maximize-minimize equation, and that's the one we'll take the derivative of. The other one I like to call your constraint equation, also known as the secondary equation, and that puts kind of a constraint on your information. So it says find two numbers whose difference is 100. Okay, so what does that mean? Difference is 100. Well, difference means subtract. So when I subtract the two numbers, it's 100. Now, what do you want to call the numbers? How about x and y? So we know that x minus y equals 100. Now, that's not the equation we're trying to maximize or minimize. That's our constraint equation, aka our secondary equation. Now, what are we trying to maximize or minimize? That's the product. It says the product is minimum. What does product mean? Well, product means to multiply, right? So we're going to multiply these two numbers. Now, I'm just going to call that, you could call it P for product. That works, right? Now, that's the guy that you need to maximize. If you notice, we've already done the first couple of steps. We used variables to represent all of our information, and we created two equations. We know which one is our constraint. We know which one to maximize or minimize. Now, the next step is always the same. What you need to do is solve for either variable in the constraint equation. This one right here, x minus y equals 100. So you can solve for x or y. It does not matter. I'm going to solve for x only because x is already positive right there. So we know that x is equal to 100 plus y. I just moved that y to the other side. You with me? So now the next step, so this was the solve step. Now we're going to substitute. So I'm going to take 100 minus y and plug it in for that x right there. So I'm going to put my p on the other side because it makes me feel better. So p is equal to, remove the x and replace it with 100 plus y times the y that's already part of the product. And again, this is your maximize equation. So that step was a substitution step, and now we have our equation. Now you might want to simplify your equation a little bit. Remember what you're going to have to do with it. You're going to have to take the derivative, and you're going to have to find critical numbers. So if you wanted to take the derivative as it sits, you could use the product rule, but why go through all that grief when we can just distribute the y inside and say this is 100y plus y squared. And now I'm going to take the derivative. So p prime would be good notation. We're taking the derivative of p with respect to y, okay, if you wanted to use other notation. But the derivative of p would be 100 plus 2y, just using the power rule right there. Now what am I supposed to do? I'm supposed to find critical numbers. Remember how to find critical numbers? There's two different things you must do. You must set the derivative equal to 0, so p prime equals to 0. And where is p prime? Undefined. Okay? Well, p prime is equal to 0 at 100 plus 2y. I'm going to solve by subtracting the 2y over and then divide by negative 2, so y is negative 50. Where is that equation undefined? It's not. It's not. There are no variables in the denominator. Nothing to be concerned about as far as undefined. So this particular situation doesn't have an undefined. So we have an answer that y is equal to negative 50. Now what I didn't address in the middle of the problem was really the domain of our maximize-minimize equation. So we could go back right here. That's our maximize-minimize equation, right? And talk about what's a realistic answer for p, or our numbers in the end. Now it says find two numbers. It doesn't say they have to be positive or negative, whose difference is 100 and whose product is minimum. Okay, so You know, there are no restrictions. It doesn't have to be just positive numbers. Oh, and notice I said I was going to maximize that equation. Let's go back and fix that, y'all. You probably noticed I'm not maximizing at all. I need to minimize this equation. I'm not following the directions. Now, did you notice that didn't make any difference in our results? Remember, you're coming up with critical numbers so far, so we're not finished, okay? Now, do we have a bottom or a top to these values? When we talk about our x's and y's, okay, well, it just says to find two numbers. They could be positive or negative. What's the biggest that number could possibly be? Well, if the difference is 100, I guess, 0 minus 100, the difference is 100. So the biggest value it could be is 100. What's the smallest value a number could be? Well, negative 100, right? I mean, anything bigger than that, it's not going to give you a difference. Oh, yeah, it will, right? Well, 200 minus 100. So we really don't have a top and a bottom, because we could do 1,000 minus 990. That's still two numbers whose difference is 100. Okay, so there's not really a maximum or a value or least value on our domain, but we did find a critical number. Okay, now once you found your negative 50, that could potentially be your answer. You would have to plug in the endpoints and your critical number. Well, once again, let's discuss. We don't really have any endpoints in this situation. We know that you think about the biggest number x could be, well, it could be an infinite number, because you can always take a number and subtract something from it and get 100. And not 990, but 1,000 minus 900 is 100. I was thinking 10, I'm sorry. So there is not a max nor a minimum value. So there are no endpoints that we have with our constraint situation. So if y is negative 50, then what would x be? So we need to find x. Now, how do you find x? Well, a couple of things. We know y is negative 50, so we could go to our original constraint equation, or we could go down here where we have x is equal to 100, and then plus, y is negative 50. So x in this situation is positive 50. Okay? Now, let's think about this. Does this really actually make any sense? If x is 50 and y is negative 50, okay, or that's our two numbers, would that give us the minimum product? And by the way, what is the product? Okay, now notice it didn't ask for the product. It says find the two numbers, but what is the product? If you multiply 50 times negative 50, you get negative 2,500, right? Now, does it make sense? Is that the lowest possible product that you could get if you multiply numbers together that subtract to give you 100? Okay, well, what if we did like, 200 minus 100 would give us 100, right? Well, 200 times 100 is way bigger than negative 2,500. Or you could do 0, right? 100 minus 0 is 100. 100 times 0 is 0. That's definitely not bigger than negative 2,500. So think through your answers. You could think about negative numbers as well. Like, if you were doing, what would the difference between, say, negative 50 and negative 50, see, negative 50 minus 50, would be negative 100. That wouldn't even work. So again, think about, I'm going to talk myself into a hole. Think about every possible combination of numbers to subtract to give you 100 that pops up in your head. There's no way in the world you're going to find two numbers that multiply together to give you any lower than this. Now here's another thought. Could I ask the same question and say product is maximum? Like, we want two numbers that subtract to be 100, but their product is as big as it possibly could be. Think about that for a minute. Not possible, right? That has a limit of infinity. You could do, like I did a minute ago, 1,000 and 900. Well, 1,000 times 900. You could do it bigger than that. 2,000 times, 1,900, right? and that's still a difference of 100, but the product gets bigger and bigger and bigger. So there is no way I could ask the question, what is the maximum? The only question that could be asked here is, what is the minimum? All that to say, think about your answer and make sure it makes sense. So let's try another one, okay? So this time we want to find two positive numbers. So notice that they say positive, so any negative values we get don't apply. Find two positive numbers whose product is 100 and whose sum is minimum. So we got another minimum situation, but this time the sum is minimum. So our constraint equation, two positive numbers whose product is 100. So how about we do x times y equals 100? And again, I call that my constraint. Your current book calls that your secondary equation. Well, what's the primary equation? The main equation, the one you want to maximize or minimize, and that's a sum. You know how to find a sum, you add. So x plus y equals, and I'm just going to call it S for sum, or you call it M for minimum, whatever makes you feel better. So that's my two equations. This is the one we want to minimize. I try to always label that. Last problem, I labeled it improperly. I put maximize, but we really want to minimize. Now, I need to solve for x or y in the constraint equation and substitute into the max and min equation. So I think I'm going to solve for y again. So if xy equals 100, then x is equal to 100 divided by y, right? So that's the solve step. The next step is the substitute step. So I'm going to take that 100 over y and plug it in for my x value. So I have 100 over y plus y is equal to s. You remember, this is the guy I'm supposed to minimize. I need to think about my domain of this function. Well, one thing is it can't be 0, right? And look, originally, it's not going to work out if it's 0 anyway. There's no way you can multiply two numbers together to get 100 if one of them is 0. So the smallest number it could be is not 0, is anything a little bigger than 0, okay? Now, what's the biggest number you could possibly have? Okay, well, we're trying to minimize a sum. There is no maximum value, so this really goes from 0 to infinity. So we don't have any endpoints in this situation again. So one of the guidelines I talked about, you got to check the endpoints to find a max or a min, but we don't have a maximum value for this particular situation. You could even have a number over 100, right, and multiply by a fraction. We just got to remember that our answers need to be positive. So what do I do next? I need to take the derivative. So s primed equals the derivative of 100 over y. Maybe I want to rewrite that, right? So instead of saying 100 over y, let's call it 100 y to the negative 1 plus y. So when I take the derivative, I'm going to have negative 1 in front, so it's negative 100 y to the negative 2 plus the derivative of y is 1. There's my first derivative. What am I supposed to do with that? I'm supposed to find the critical numbers. So two things I got to do. I got to find out where the function is undefined and where the derivative is equal to 0. Okay, so where is it equal to 0? Well, I'll have 0 equals negative 100. I'm going to write that over y squared plus 1. And to solve that equation, I'm going to subtract the 1. How about let's add the 100 over y squared? That feels better. Multiply both sides by y squared. Take the square root of both sides, so y is equal to plus or minus 10 when I do the algebra, right? Because I took the square root of both sides. When you take the square root, you got to put a plus or minus. We did that, but now I know what you're thinking. At least I hope that's what you're thinking. The negative 1 doesn't apply, right? I'm going to put two negatives. I don't want that. The negative 1 does not apply because it says the numbers have to be positive. So I'm only going to consider the one critical number of negative 10. The next situation I got to consider is, where is this derivative undefined? Now we know, and we can look at it right here if you'd rather, that y cannot be 0 in this particular situation, but that was not on our list in the first place. Our original function was not defined at 0, so I don't really have to consider y equals 0. My only critical number is negative 10. Now what do I do with my critical number? Well, I'm supposed to plug it in And the largest of the numbers I plug in, including endpoints and all critical numbers, would be the maximum, and the smallest would be the minimum. We only have one number, which must be the minimum, or they've asked us the wrong question in this problem. So I take my negative 10 and I need to find x, okay? So if y is negative 10, then what in the world is x? And so I have right here, x is equal to, it's not negative 10. I keep writing a negative. It's positive 10. Goodness gracious. So x is equal to 100 over y, so x is equal to 10. So we have our two numbers. They're both 10. Now let's think about this. So find two numbers whose product is 100. So that means you multiply them together and get 100. But their sum is the smallest it could possibly be, in other words, the minimum. Okay? Well, the product of 10 times 10 is 100. The sum, 10 plus 10, is 20. Now think about other numbers that multiply to give you 100. Like, for example, 50 times 2. Okay? Well, what's the sum of 50 and 2 is 52. 20 is smaller than that. Or what's something else that gives you 100? How about 20 and 5? Well, 20 plus 5 is 25. So you could see where 10 and 10 are going to be the smallest numbers that multiply to be 100 and also sum to be the smallest it can be. Okay? So that's our result. We found the two numbers. Now let's try something just a little step up from that. All right, so we got a garden. It's to be laid out in a rectangular area with a limited 100 feet of fencing. In other words, all we have is 100 feet. That's it, no more. What are the dimensions that will give the largest possible area? Because if you're going to build a garden and you only had 100 feet, you would definitely want it to be the biggest it could possibly be, right? All right, so we have a garden laid out in a rectangular area. One of the guidelines should have said draw a picture. Now, the last two problems we had, we certainly couldn't draw a picture to represent that information, but this one we can. Okay, so I have a rectangular garden, so clearly I need to draw a rectangle. Okay, I have 100 feet of fencing. Okay, so all the way around this guy is 100 feet. This is what are the dimensions that will give the largest possible area. Now, one of those guidelines says you need to label or assign a variable to all the unknown information. Now, you can certainly use x and y if you want to, but you might feel a little better calling this the length or this the width. Does this one have to be length and this one w? Well, not at all. You could call this this L and this W. You could call this length and height, whatever you feel better about. I promise in the end, it's not based on your variable you selected. It's based on your calculations. So, let's come up with our two equations. You want to? So, we know that we only have 100 feet of fencing. So, I have L plus W plus another L plus another W is equal to our 100 feet. I know you know this. That is 2 L's plus 2 W's is equal to 100 feet. That is our constraint equation. The equation that's typically equal to a fixed value is your constraint equation, but I will tell you the truth, not always. The best way to know your constraint equation is the one that you're not maximizing or minimizing. Again, the book calls it a secondary equation. Now, the equation that you're trying to maximize or minimize is area. We want the largest possible area. You know how to find the area of a rectangle. It's area is equal to length times width. And I remind myself that that's the guy I'm trying to maximize or minimize, which is maximize in this particular case. Now you can see that to maximize this thing, there's a limited amount of fencing, so it's going to have a maximum. Whereas if I asked you the minimum of this problem, it would be kind of silly that you would have no length or no width and the area would equal to 0, right? So you just have a long 100-foot strip of fencing with no garden whatsoever, which is silly. So often you can only ask what is the maximum or what is the minimum based on your particular example. So anyway, let's solve for either L or W in the constraint equation, right? So it doesn't matter, solve for L, solve for W. I'm just going to solve for L only because it's written first, okay? So I've got 2L is equal to 100. I'm going to subtract that 2W to the other side and then divide everything by 2. So your length is 50 minus Does that sound okay? I'm going to square that off so it's easy to find later. Now, what am I going to do with that? Don't forget, you've got to substitute that into your maximize or minimize equation. So if that's L, then I'm going to plug it in right there for my L value. So now I have area is equal to, in parentheses, 50 minus W times W for the W that's already there. And that's the guy I want to maximize. Now again, let's think about our endpoints, okay? Length and width can't be any smaller than 0, okay? So 0 is the biggest. What's the biggest, the smallest? What's the largest you could be dealing with? Well, I guess 100, right? Because you don't have any more than 100 feet of fencing. So if the length were 100, you can't make it any more than that because you don't have any more than that. So you do actually have endpoints in this situation. I'm going to go ahead and tell you the truth. Those are going to minimize it. We've already talked about it, but we will formally check that in a minute. All right, so here we go. Take the derivative. But before I take the derivative, maybe let's distribute that W inside. So 50W minus W squared. So here I go. A primed is equal to the derivative of 50W is 50 minus the derivative of W squared is 2W. What am I supposed to do with that? I'm supposed to find the critical numbers. Critical numbers are found by two ways. First of all, setting the derivative equal to 0, and also where the derivative is undefined. Okay, so equal to 0, we're going to add the 2W. I'm going to divide by 2, so W equals 25. I'm going to circle that because that is a critical number. Now, I'm not saying it's my answer, but it's definitely a critical number. Now, when you look at the derivative, y'all, there's nowhere that this thing is undefined. It's a polynomial, 50 minus 2W. There is no W value that would make that function undefined. So that is not part of our situation here. Now, we actually have some endpoints for this particular problem. So we're trying to find the absolute maximum. So to do that, I take my endpoints and plug them into my where are you? Right here. Your maximize minimize equation. So to find the absolute max or the absolute min, you take our endpoints and our critical number. So I'm going to evaluate the area at 0. So it's 50 times 0 minus 0 squared. So that equals to 0. Okay. And then I'm going to plug in 25. So that's 50 times 25 minus 25 squared. I'll do that calculation in a minute. And then 50 times 100 minus 100 squared. I wrote that all wrong. All right, so let's run our numbers. You want to? So you got 50 times 25 equals that minus 25 squared, and that gives me 625. And then I have 50 times 100 minus 100 squared, and that gives me negative 5,000. Well, that's just wrong, right? We have an area that's negative, so that's not happening. That situation doesn't even make sense. The biggest of these values is your 625. The smallest of these values is your minimum. It didn't ask for the minimum, it asked for the maximum, okay? So I'm asking for the dimensions. I'm sorry, I just had a brain it stopped for a second. So I'm asking for the dimensions and the largest possible area, okay? So the dimensions are, we've got 1, right? We've got 25, and that was our width. What would our length be? Well, you have to go back and plug it in. That would be 50 minus 25, which is 25, okay? So we have width is 25, length is 25, and then the area, again, area is length times width, which is going to be 25 times 25, which we had already found is 625. Now, we probably need to be using units, don't we? It was in feet, so this is 25 feet, and right here we have 625 feet squared. Okay, so pretty straightforward. We got one critical number, but thinking about these limits, you know, kind of like endpoints can get a little bit strange. But again, if you think again, the smallest that your width could be 0. It doesn't make a lot of sense because you wouldn't have any area. Your biggest your width could be would be 100. But fact is, that would take you back down to 0. Okay. Another point I should probably make is that if you think about it, if you have a rectangular situation, the way to maximize the area is with a square. That makes pretty good sense, right? If you're just drawing a rectangle, the way to make the biggest area is to make the length and the width the same. That gives you a square. Okay, I'm going to wrap up this video, but I'm going to come back with slightly more challenging problems, some more examples to help you out with this optimization process.